Hello and welcome to our class. I hope all of you are well and just trying to adjust to being at home all the time. All right, so first thing, I'm happy to see everyone who's here. Thank you for being here. First question is, are there any homework questions?
Yes.
All right.
5.3 was a little tough for me.
Okay. So what questions are there for 5.3?
I have number 13 and 19.
13 and 19?
And 21.
And 21. Okay. Any others from chapter 5, 5.1, 5.2?
No, I think, yeah, no.
Those were it? Okay, let's start with those homework questions. So I'm going to go ahead and share my screen. Screen share. All right. .3 number 13. All right, so to begin, you want to make sure you have your formulas handy. So make sure you take a look at 5.3 and have that first page where all of your formulas are there. That's what's nice about this book is that it has all of it just in one easy spot for you to find. So you have all of them right here, right? All of your formulas. Because we have tangent and because it has a fraction, we know we're going to use one of these. Now the main difference is that plus on top. If I have a plus on top, it's going to be this formula. If I have a minus on top, it's going to be this formula. Okay, let's go back to our question 13. Okay, I have a plus sign, right? So I'm going to take the time to write our formula. Our formula is tangent of A plus B is equal to tangent of A plus tangent of B all over 1 minus tangent of A tangent of B. What does our instruction say? It says use a sum or difference formula to evaluate. All right, so because we have a plus, I know that if I let this be A and I let this be B, I can rewrite it as tangent of 150. And is that a value in our unit circle? Take a time to like scramble through your word. Pardon?
Is it negative 2 square root 3 over 3?
Give me a second, let me find the unit circle. I don't know tangent by heart.
Oh, no, you're fine. I thought you were asking us. I'm sorry about that.
Oh yeah, I was, but as I was asking, I was like scrambling through my files. Cheat sheet. All right, so tangent of 150. 150 has a reference angle of 30. Tangent at 30 is square root of 3 over 3. But because it's in quadrant 2, only sine and cosecant are positive, that would make it negative. Is that what you got?
Yeah.
Yeah, cool. So this would be our answer.
That's all I had to do. I think I was overthinking it because, I don't know, I think it's because it's tangent because I was able to do the other ones, but not this one.
Oh, okay.
Yeah. I was just
that makes sense. Yeah, so think of it this way. If it's written the long way, it wants you to use the short way to come up with it, because it would be a pain in the butt to find tangent of 120 and then add it to tangent of 30 and then do all that work. So it's saying, hey, isn't it much easier to do tangent of a plus b, so 120 plus 30? That's easier. That gives me 150. That's a number in my unit circle. It's in quadrant 2, right? Has a reference angle of 30, and then you look at your chart. When's tangent 30? I mean, tangent of 30 is radical 3 over 3. Because we're in quadrant 2, it's negative. All right, another question was 19. Same deal, right? But now we have radians. So we have, because I have a minus, that gives you a, that's the big indicator which we're going to use. Our formula would be tangent of a minus b is equal to tangent of a minus tangent of b all over 1 plus tangent of a tangent b. Okay, cool. So we're going to let a be radical, 5 pi over 3, and we're going to let b be pi over 6. So I can use a shorthand, and this would be the same thing as tangent of 5 pi over 3 minus pi over 6. All right, let's do that work. We need a common denominator. Then you multiply the first by 2 over 2. So we get 10 pi over 6 minus pi over 6. And get 9 pi over 6. It simplifies to be pi. They have a common factor of 3, so 3 pi over 2. Now we're asking ourselves, what is tangent of 3 pi over 2? Okay, we take a look at unit circle. 3 pi over 2, that is 270 degrees. That's that bottom coordinate. And tangent at 90 is undefined. So it's also undefined. So even though you're like, how would it gone undefined? Well, somewhere along the denominator, something would have happened. Maybe that would have added to be 0 or something like that. And it would have made that entire fraction undefined. That's what my guess is. Something would have happened to it to where you would have gotten 0 on the bottom. All right, that was 19. 21. You want to verify? Okay, we're going to verify the right-hand side and the left-hand side are equal. So we're going to use this hint right here. We're going to use a hint that sine of negative pi is the same thing as 0 minus negative pi. Sine of negative x is the same thing as 0 minus x. Sine of 0 minus x. Okay, well, let's go ahead and replace the inside negative x with 0 minus x. So I have sine of 0 minus x. Okay, now let's go ahead and use that sum and difference rules for sine and cosine. So that formula reads to be sine of a minus b is the same thing as sine of a times cosine of b minus sine of b times cosine of a. Let this be a and let this be b. Let's make that substitution so that we have sine of a is 0 times cosine of b, b is x, minus sine of b, sine of x, times cosine of a, cosine of 0. Okay, now looking at the circle, what is sine at 0? At 0, sine is 0, so I'm left with 0 times cosine of x minus sine of x, and what's cosine of 0? At 0, cosine is 1, so sine of x times 1. Or anything times 0 is 0. So for our answer, what are we left with? We're left with negative sine of x. That's it. We have shown that negative sine of x is the same as negative sine of x. So this is making you go through the process of proving those correct functions, those correct formulas. Not correct, co-function.
Yeah,
I'm sorry, I didn't mean to cut you off. What were you saying?
Oh, for the other ones, I was having trouble working with the x's because I wasn't exactly sure what to do with them or what to do with them.
Just keep it as an x. Don't try to, I mean, you're not solving for x. That's our next chapter. We're just trying to work with them, prove that they're equal or manipulate in some way. So maybe you're thinking that there's a number to working with. There's no number. We're just trying to make these two look the same. And we're using that I can rewrite negative x as 0 minus x. And that helps us use this formula. That's the whole purpose of it. If I have two numbers that are being added and subtracted, I can use that sum and difference formula. And by doing so, we see that, hey, well, a whole side of our equation, or I'm sorry, of our expression is gone. So we're just left with the second term, which gives us our right-hand side, that negative sine of x.
Oh, okay. Thank you so much.
I know they're weird. You're welcome. Alrighty, any other questions?
Yeah, I had some issues with 23, 25, and 27, actually.
All right, 23.
It looks like it's simple.
Yeah, I was the same on 23. That was pretty difficult.
All right, same section?
For me, yeah, it was 5.2 on this one.
5.3?
Sorry, yeah, 5.3. I looked at the wrong chapter.
It's okay. All right, so 23 reads, use a sum or difference formula to verify each. Okay, so I want to show that these two are the same. Okay, well, you have your sum and difference formula at the beginning of your section. You have these loose leaves. I would have this loose leaf out as I'm working through your homework. So sometimes when we're given something in this way, it doesn't really help us with anything really. So we have to make it a point to rewrite it. So we write it using that longer method. So that's what's going to help us move through those problems. So let's jump back to our book, 23. At the end, there's those proofs. All right, 23. Okay, so I want to verify. I want to show the right-hand side and the left-hand side are equal. Always work with the more complex, and we see that these are much complex, right? So let's work with those. Okay, I'm going to use my sum and difference formula for this one only. Okay, I'm going to rewrite it where my 90 is going to be A and my B is going to be the X. So let's rewrite it using our formulas. So that ends up being a sine of 90 times cosine of X. Did I start off? Yeah. Plus sine of B, so sine of X times cosine of A, cosine of 90. That's my first one. Then I'm going to add plus I might run out of space, so let me make it smaller, bigger. Plus, all right, the next one in blue, or I'll use some other color, use purple. Let this be A and let this be B, and now we have a minus. So I have sine of A, so sine of 90 times cosine of B, cosine of X, minus sine of B, sine of X, times cosine of A, cosine of 90. Okay, let's evaluate where we can, especially where we have those degrees. So I can evaluate for all of those that have a degree. Let's go ahead and rewrite it. So sine of 90, that gives me 1. So we're left with 1 times cosine of X plus sine of X times what's cosine at 90, that gives us 0, plus sine of 90, that gives us 1 times cosine of X minus sine of X times cosine at 90, and that gives us 0. All right, whenever we have anything multiplied by 0, that gives us 0. So those are done. Those gave us 0. So what are we left with? We're left with, well, 1 times cosine, that just gives us cosine of X, plus 1 times cosine of X, that just gives us cosine of X. Cosine of X plus cosine of X. If you're ever confused, you can always stop for a moment and you can think, well, what's X plus X? When you say that's just 2X. All right, so that gives us 2. 2 what? 2 apples, 2 cosine of X's. And that's what we wanted, right? So we have 2 cosine of X is equal to 2 cosine of X.
There you go. Yeah. Okay, that makes sense. I couldn't figure out that what I needed to do was write each one of those long ways and then put them side by side and add them together.
I get it. All right, let's take a look at 25. All right, same thing here. I want to show they're equal. Let's look at the more complex side. All right, I see sine, and I'm working with two numbers that I wish I could, in a sense, kind of rewrite. So we're gonna rewrite it so that I have sine, I have a minus. I'm gonna write this to be, I'm gonna write my formula. If that's A and that's B, sine of A minus B, that gives us sine of A times cosine of B minus sine of B times cosine of A. Okay, now to write it with our A's and our B's. So A is 90 and my B is X. So I have sine of 90 times cosine of X minus sine of B, which is X, times cosine of A, and A is 90. All right, let's go ahead and evaluate. Sine at 90, we get 1. So I have 1 times cosine of X minus sine of X times cosine at 90, and cosine at 90 is 0, times 0. Anything times 0, it always is 0. So we're left with just 1 cosine of X, which is just cosine of X. So we have proof that cosine of X is equal to cosine of X.
I've only just realized that's one of the negative angle identities, I think.
Yeah, we have those. We have these right here as the other formulas. He has them called as negative angles. Other textbooks call them cofunctions, I believe. I know this book calls things differently than what other books call it. Let me scramble through my books. Yeah, these are called cofunctions. And I think if you want to look these up, cofunction is what they're usually called. Those are your cofunction identities. All right. Now he doesn't give you all of them, which I feel is so weird. I'm gonna email you guys a page of all the formulas, but it's from another book. So they're gonna look a bit different. For 27, I don't think you have all of the tools to do 27. So, but let's try it. Let's try it with what we have from our author Bob. So maybe we should try writing it as sine and cosine. So secant comes from inverse of cosine. So that gives us 1 over cosine of 90 minus x. And I think that's how we can work it out with a 1 over. All right, let's go ahead and use our sum and difference formulas for that cosine of 90 minus x. So we have 1 over, let me write down my formula above that we're going to use. Cosine of a minus b is the same as cosine of a times cosine of b plus sine of a sine of b. All right, so if this 90 is a and the x is b, we can rewrite it to be cosine of a, which is 90, times cosine of b, which is x, plus sine of a, which is 90, times sine of b, sine of x. All right, well, cosine at 90, that's 0. So I'm left with, let's rewrite it 1 over 0 times cosine of x, plus sine at 90, that gives us 1 times sine of x. Well, this is gone, anything times 0, we get 0. So we're left with 1 over sine of x. And sine of x, the inverse is cosecant. So we have now proved that cosecant of x is equal to cosecant of x. Now, let me share a sheet with you, and this is what I'm going to email you. It has everything, a lot more than what your current book gives you.
I watched his video on this section, and he didn't mention anything that would have helped with that one.
Yeah. What he does is he really emphasizes the basics so that you are always in a situation where you can get out of trouble. And that's cool because you kind of know less, but you can develop the rest. And I think that's cool. All right, so what am I looking for? I'm looking for cheat sheets.
And they say my every day, not only day, oh Lord, to me, oh Lord, tell me.
Is someone singing? All right. So this I'm going to send you. It has all of your cofunction identities. And we were given the first 2 only. You're missing the rest, but you can always develop the rest using the idea of a reciprocal, like we did in our last problem we did together. All right, let's go ahead and continue with our notes for today, 5.4. Now we're going to work with double angle identities. And this is our last section of chapter 5. Then we're going to jump to chapter 6. All right, double angle identities. So let's read our textbook together. What is a double angle? Stating the obvious, a double angle is 2 times. So 2 times theta. Is any angle measured that is twice another angle, theta. So 60 can be thought as a double angle because it is twice of 30 degrees. Likewise, 45 is a double angle because it is twice of 22.5. However, the real value in identifying a double angle is between it is being compared to a non-doubled angle. We saw this in the previous chapter. The graphs of y equals sine of x and y equals sine of 2x are distinct but related. These graphs have different frequencies and different periods, but the amplitudes, y-intercepts are the same. But it may be obvious and it's important to note that theta and 2 theta are different angles and sometimes terminate in different quadrants, as demonstrated below. If theta is in quadrant 1, then 2 theta can be written in quadrant 1 or 2, depending on whether theta terminates before or after the 90-degree mark. So it's saying that we can have either this red slice, right? Or we can have this smaller slice in blue, but they all come together are the same if you're looking at it as 2 slices. And where it matters is in our argument. So focus on these 2 arguments. Notice how we go from just that 1 theta to a 2 theta. When you multiply by 2, you multiply your entire equation by 2. So 90 times 2 gives you 180. 135 times 2 gives you 270. So that plays an important marker on our argument. As it also explains in the next section. So depending where our argument is, it affects where our theta should end and start. All right, let's continue with page 312 with double angle identity for sine. The double angle identity is a formula for an argument that is twice the value, such as 2a, 2 theta, or 2x. We use the sign of a sum formula to develop a double angle identity for sine. So sine of 2a would be the same as sine of a plus a. So here, this is kind of like your proof of it. How does it work? All right, so I can use my sum and difference formulas from last section. So we can now say that sine of 2a is the same thing as 2 sine of a times cosine of a. And you have the reasoning, your proof right above. So that's one of your formulas. To confirm the double angle identity for sine, we show that it works for some known values. So find sine of 60 by treating 60 of twice of 30. So here we're going to do some examples just to show you that it's true. So we can know sine of 60, that's a value in our unit circle. So we don't need to go through the process of doing this. But just to make sure to show you that it is true, let's treat it using our formula above. I can treat it as 2 times 30, or twice of 30. So in this case, A is 30. We already know that sine of 60 is radical 3 over 2, so the double angle formula should give us that same value. So we're going to treat it as 2 times 30, and we're going to use our formula that says I'm going to multiply it by 2 times sine of A cosine of A. So 2 times sine of A cosine of A. Your A is 30. So that we have 2 times cosine of 30 is 1/2, and sine of 30, cosine of 30, sine of 30 is 1/2, and cosine of 30 is radical 3 over 2. All right, multiply them together, and we're left with radical 3 over 2, which is what we knew we should get, because we know that sine of 60 is radical 3 over 2. All right, let's do another example. Let's do in class example 2. So let's find sine of 270. Now we know what this is. If we look at unit circle, we know that sine of 270, if we look at our unit circle, that gives us -1. But let's think of it as 2 times A. So 2 times 135. So we have sine of 270 is equal to a sine of 2 times 135. All right, and we have a formula for something that looks like this. We have it right above. If it's 2 times something, we can write it as 2 sine of A cosine of A. Well, let this be our A. So we can write it as 2 times sine of 135 times cosine of 135. All right, at 135, sine is radical 2 over 2. And at 135, cosine is negative radical 2 over 2 times that initial 2. Let's multiply them together. We're going to have negative. We're going to have 2 times radical 2 times radical 2 all over 4. So we're left with 2 times 2 over 4, which gives us -4 over 4, which gives us -1, which we knew would be our answer because we know that sine at 270 gives us 1, as we wrote above. And that's what we got. And I might feel silly doing it with something you already know the value of. So I'm sure the next one will give us something that doesn't work out. So let's skip you try it 1. All right, it's going to make us go into cosine. The double angle identities for cosine. There are 3 double angle identities for cosine. A basic identity and 2 others are derived from the basic identity. We use the cosine of a sum formula to develop the basic double angle identity. Cosine of 2a equals cosine of a plus a. So if we use our sum formula, we get this. This is our little mini proof. So we have cosine of 2a equals cosine squared a minus sine squared a. All right, so here it gives us a formula where we kind of use it with an angle we already know. There's another one. Using Pythagorean identities, cosine squared of a is equal to 1 minus sine squared of a. And B, sine squared of a is equal to 1 minus cosine squared of a. You can generate 2 other identities for cosine of 2a. All right, so we're going to replace that cosine squared with our Pythagorean identity. And if so, we have a brand new one. And we can do the same thing with the other one. I can replace sine squared of a with 1 minus cosine squared of a. and we have another identity. So we have 3 total cosine of double angle formulas. Okay, let's do in class example 5. Find cosine of 240 by treating 240 as 20 as twice 210. Use each variation of the double angle formula for cosine. All right, so we have 2 formulas it wants to try. We'll do one of them. Let's do A. So we have cosine of 2A is equal to 1 minus 2 sine squared of A. So we're treating this as cosine of 2 times, instead of 240, we write 2 times 210. And our A is at 210. So that we have 1 minus 2 times sine squared of A, and A is 210. So we have 1 minus, well, what's 210? What's sine at 210? We look at unit circle, sine is your y, so we get negative 1/2. And that's going to be squared. I know I'm trying to make 2 so funny. It's going to be squared. All right, negative 1 squared is 1/4. So we have 1 minus 2 times 1/4. 2 times 1/4 gives us 2/4, which is 1/2. So 1 minus 1/2 gives us 1/2. That would be your answer. And you can check it because 420 is a value in your circle. So cosine of 420, let's subtract 360. That's the same thing as 60. And cosine of 60 gives us 1/2. So it checks out. That's what we got. So it's making you practice with numbers that you can evaluate without using these formulas. So when would it be helpful? It'll be helpful when we'll have some values that are not in the unit circle. But if I double it, I can work it out. And that's the point of it. Now we also have some double angle identities for tangent. But the double angle identity for tangent likewise developed from the tangent of a sum formula. So we have tangent of 2a is equal to tangent of a plus a, which we use our formula from 5.3. And therefore we're left with our formula. Tangent of 2a equals to tangent of a over 1 minus tangent of a. All right, now for this same idea, I want you to think of twice as of an angle you already know. I'm not going to do those because those are weird. Not weird. I don't like them because they're confusing because they're making you work with a number that is within the unit circle. So why would you use the tangent formula? It's just for practice. Applying double angle identities. We can use double angle identities to explore the relationship between an angle and its double. For example, we know that sine A is 3/5, so what's sine of 2A? To find the value of sine 2A, we must know both the values of sine and cosine. If we first know the value of sine A, we can use Pythagorean theorem techniques to find cosine of A. Either use the Pythagorean identity to show that cosine of A equals plus or minus 1, the square root of 1 minus sine squared of A, or use the xy plane relationship, cosine of theta equals x over r, sine of theta equals y over r, and tangent of theta equals y over x. And x squared plus y squared equals r squared. All right, example 7. Given that A is in quadrant 2 and sine of A is radical is 3 over 5, find both sine of 2a and cosine of 2a. All right, so let's go ahead and use our formulas. So sine of 2a, let's write above. Sine of 2a is equal to 2 times sine of a times cosine of a. All right, now what are we given? We're given only the sine of 3 over 5, sine of a. Cool, I have a sine of a right here, but also need a cosine of a. What about my cosine squared of a? We have options. We have 3 different options for cosine of 2a. One of them only uses sine, so I don't need to worry about it too much because I know for cosine of 2a, I have one that only deals with sine. So 1 minus 2 sine squared of a. I have sine of a, and I only need a sine of a. Okay, so I need to do some work to find cosine. How can I find cosine? All right, let's read through our procedure. Solving for sine of 2a and cosine of 2a is a multi-step process because we are given sine of a, which is 3 over 5. It must be that y is 3 and r is 5, right? Remember, sine of theta is y over r. So if we have 3 over 5, y is 3 and r is 5. We can use Pythagorean theorem to solve for x. Use this outline to solve. We first want to find our values x, y, and r. So we have y and r, we need to find x. We need to find x by using the Pythagorean theorem to find our third value, which is 2. Okay, now this is the part that you always have to stop and think. X is the square root of 16. Whenever you take the square root, you have to write plus or minus. But because A is in quadrant 2, it tells us that we're in quadrant 2. Think of quadrant 2. All students take calculus. Because we're working with quadrant 2, well, we're not working with that. Because we're working with quadrant 2, we have an r of 5 and a y of 3. Your x has to be negative. So we choose -4. All right, now for 3, we now have cosine. Cosine is x over r, and we have our x and our r, so we have the fraction of -4 over 5. And we're given sine. So now I have enough to use these formulas that we want to evaluate for. We want to evaluate for sine of 2a and cosine of 2a. For sine of 2a, we were missing the cosine, and that was crucial to solving and using our formula. But now we have our cosine, so we can use our formula. We have 2 times our sine. We were given sine. Sine is 3 over 5. And cosine, we found cosine is -4 over 5. We plug them in and we get our answer. For cosine 2a, I never needed sine because I could have used cosine of 2a, which only has a sine squared. But you can use any one of your formulas. Here they use one with the sine. You get an answer of 7 over 25. Let's do example 8. Given sine of a is equal to radical 2 over 3, find cosine of 2a. For our procedure, we have 3 options for the identity of cosine 2a. So we could choose one that is easiest to work with based on the given information. Because we know the value of sine a, we can use identity 2a, which requires a knowledge of the value of sine a only. So our goal is to find cosine of 2a. You have 3 different formulas to pick from, and here it's saying we have one that only has to deal with sine. We're given sine, so there is nothing that we need to do other than to use our formula. All right, so sine of A is radical 3 over 2. We square it, we multiply it by 2, and we subtract that from 1, and we get our answer. Let's do another example in class example 9. Let's do this one together. Given A terminates in quadrant 4. All right, so we're going to be working with quadrant 4. That's our triangle. And tangent is negative 2 over radical 5. We call that tangent of theta is phi over x. Find both sine of 2a and cosine of 2a. Use this outline to solve your work, and it kind of helps you to do each one. Okay, for tangent, I have, so we have some work to decipher. Tangent of a is negative 2 over square root of 5. Okay, so we have y over x for tangent. So my y is negative 2, and your x is radical 5. We're left to find this r. We don't know what it is. I can use it, I can find it by using my Pythagorean theorem. X squared plus y squared equals r squared. All right, let's fill in some values. So my x squared, I have square root of 5 squared plus y squared, negative 2 squared is equal to r squared. 5 squared is 5 plus negative 2 squared gives us positive 4. That gives us r squared. 5 plus 4 is 9. R squared. So we're left with the square root of 3. I'm sorry, I ahead of myself. The square root of 9 is equal to r plus or minus. Do we want plus or minus? Well, r is always positive. Your hypotenuse is always positive. So I would want 3. R is equal to 3. Okay, now we have cosine. Cosine is found from x over r, and sine is found from y over r. And we have those numbers listed above, x, y, and r. So cosine of A is radical 5 over 3, and sine of A is negative 2 over 3. Okay, now I can go ahead and solve my formulas. That's the whole purpose of this. We only have one for sine. So let's write down the only formula we have for sine. Our double angle formula for sine, we have 2 sine of A times cosine of A. Let's fill that in. So I have 2 times sine of A. What is sine of A? We said sine of A is negative 2 over 3. So negative 2 over 3. All right, now we want cosine of A. Cosine of A, what's cosine of A? We found that that is radical 5 over 3. All right, let's do some work to figure this out. Remember, think of it as 2 over 1. So I have 2 times radical 5. I have negative 4 over radical 5. 1 over 3 times 3 times 3. You get 9. Cool. All right, cosine of 2a. You have 3 different formulas for a double angle and cosine. Which one do you want to use? It's up to you. Let's use 2 times sine of A times, Oh, I'm writing sine again. 2 times, doesn't matter which one I want to use. Let's do 2 times cosine squared of a minus 1. So I have 2 times cosine of a, that's radical 5 over 3 squared minus 1. So we're left with 2 times 5 over 9 minus 1. So we have 10 over 9 minus 1. Think of 1 as 9 over 9. So we're left with 1/9. That was a lot of work.
Yes, it was.
Yes, it was. So take a moment to run through this problem again in your brain, see if you can follow every step. Let me know if there's any questions about any of the steps, how they happened. Now, what is nice about these problems is you see them in past, when you see them in your homework. I do give you this chart, this blank chart. So you kind of have a step-by-step to guide you. If you can fill out all the blanks, it kind of helps you. All right, let's move forward. Simplifying expressions involving double angle identities. As we saw in 5.3, sometimes an identity read from left to right is read from left to right. For example, if we see that the expression 2 sine theta cosine theta, we can simplify it to be 2 times sine theta. Simplify each of the following using a double angle identity. Okay, so does it have the sheet where it gives us all of them together? No, huh? That's not nice, Bob. Anyone send an email to Bob, tell him he's not nice. All right, so let's take a moment to recall our double angle identities that we learned. So I'll write them right here on the side. We have 4 of them we learned so far, 3 for cosine and 1 for sine. So summary of all of our formulas so far. So we have 1 for sine, and it's sine of 2a is equal to 2 sine of a times cosine of a. That's 1. We have 3 for cosine. Our next formula, so we have a double angle identity for cosine. Cosine of 2a is equal to cosine squared of a minus sine squared of a. That's the main one. But if we can write it using Pythagorean identities, we get 2 more. Our next one is cosine of 2a is equal to 1 minus 2 sine squared of a. And our last cosine double angle identity is cosine of 2a is equal to 2 times cosine squared of a minus 1. Cosine squared of a minus 1. All right, so here's a summary of our identities for section 5.4. And that's it. That's it for this section. Well, we have one for tangent. I'm sure that's at the end. That's pretty much it. We have another section for half angle, that's 5.5, but we're not going to go through that. You don't need that for your calculus. All right, so here's a summary. Write them on a post-it on a piece of paper. You're going to be using those so that throughout your entire your entire remainder of the section. Let's go ahead and do example 10. So we want to use these formulas that we took the time to write down when I'm given maybe the right-hand side and I want to evaluate and I can double it. Okay, so let's take a look at this first one. I have cosine squared of 75 and sine squared of 75. In your unit circle, do we have 75 in a unit circle? No, right? We have 30, 45, 60, 90. There's no 75 that I've listed. So I can't find cosine squared of 75 or sine squared of 75. I don't have that. Okay, well, let's go ahead and use our formulas. Do I have a formula where I have a cosine squared and a sine squared? I do, right? Right here. So what this is saying is I can take my A and I can double it. Maybe that will help me evaluate for that value at cosine. So we can. So we can think of this as 2 times 75, as we see in our answer below. 2 times 75. 2 times 75 is 150. Okay, 150 is a value in a unit circle. So then we open up a unit circle, either we Google it or we use one of the handouts I gave you, and we see that, hey, cosine at 2 times 75 gives us 150. Cosine at 150 is radical 3 over 2, negative radical 3 over 2. And same thing for our other one. I have 2, so at B, I have 2 times sine of 5 pi over 12 times cosine of 5 pi over 12. Do I have one that has sine and cosine? 2 times sine and cosine? Yeah, that's number 1, sine of 2a. So I can think of 5 pi over 12, multiply it by 2, and we get 5 pi over 6. Sine at 5 pi over 6, again, we use a unit circle. It has the radian measure, and sine at 5 pi over 6 gives us 1/2. Sometimes an expression almost fits one of the double angle formulas, but one or more numerical values is either different than the formula or missing from the formula. The next 2 examples demonstrate how to approach such expressions. So before we go into that, recall, you can multiply by 1 and it does not change the value of your problem or your expression, right? Because anything times 1, it's itself, right? 1 times something is itself. So 1 times 5 would be 5. 1 times 100, it's still 100. So we can multiply by 1 as much as we want. Also, what's a number over itself, like 5 over 5? Isn't that 1? Or 2 over 2? Isn't that 1? So I can multiply by a 1 and not change the value. And I can use that in a clever way. So let's go ahead and look at example 1. Use a double angle identity to simplify cosine of 22.5 times sine of 22.5. So I want to use maybe one of my double angle identities. When I take a look at them, sine and cosine, I have one that would work, right? I have sine and cosine, but what about that 2? My formula, my problem didn't have a 2. How can I write it with a 2 without changing the value? Well, I can multiply by 2 over 2, right? Procedure. This expression does not exactly fit any of the double angle formulas. However, it closely resembles the double angle formula for sine. So sine of 2a equals 2 sine of a cosine of a. 2 things are amiss. 1, sine 22.5 should be written first, so change the order. And 2, it's missing the coefficient of 2. You need a 2 in the front, right? So we'll multiply by 2. We can multiply by 2 as long as we multiply also by 1 over 2. I'm sorry, I keep touching the side of the screen. This is because if I multiply by 2 over 2, which is 1, I can split my fraction as 2 times 1/2, which is also 1. So if I'm missing this 2 in our equation, I also must multiply by 1/2. Now I can highlight and put in brackets only the part I want to focus on, and I can ignore the half for a while. This is a technique that you'll often use in your calculus course. Okay, so let's put brackets on the part we want to focus, and let's ignore the 1/2 until we're done. All right, now I have something I can work with. Now I have 2 sine of 22.5 times cosine of 22.5. All right, I can use my double angle formula and multiply. And cool, I'm left at sine of 45, which is something I can work with. That's radical 2 over 2. All right, now I can work in that 1/2 that I've been ignoring the whole time. So I multiply by 1/2, and that helps me find my final answer. So the punchline is multiplying by a 1/2 and a 2. Because remember, 1/2 times 2 is the same thing as 2 over 2, which is 1. So we're not changing the value of it. We're just making it look like what we want it to look. We're forcing it to look like our identity. All right. Another one we can do, another little trick in example 12, use a double angle identity to simplify 2 cosine squared of 15. Okay, it almost looks, in the procedure, it tells us the expression is one term off of cosine 2a equals 2 cosine squared a minus 1. To create a full identity, we must both subtract 1 and add 1. So it almost looks like our formula, right? We're missing that minus 1. We don't have it. So if I add nothing to it, I'm not changing it, right? So what if I add and subtract 1? So 1 plus a minus 1, or 1 minus 1. Aren't they all 0? So that's what we're going to do. We're going to add nothing by adding 0 and adding 1 and subtracting 1. Okay, so we want this minus 1. So let's add this minus 1. But let's compensate it by adding a 1. Because in the end, what's negative 1 plus 1? It's 0. We're not changing the value, we're just making it look like what we want it to look. All right, now that you have what you want, focus on that only and ignore the plus 1 till the end. So now I can use my double angle formula, so I can multiply it by 2 times 15, which is what you wanted, to get cosine of 30. And cosine of 30 is a value in your unit circle. All right, you find cosine of 30, which is radical 3 over 2, and you add 1, and that gives you your final answer. Both of these can work. All right, let's write a brief summary for 1. We have a new technique. One of them is you can multiply by 2 and 1/2. And you do that when you're missing. When you're missing that 2 that you want, right? You must multiply by 2 and a 1/2. Our second new technique is I can add and subtract 1. And you're doing that when you're missing a -1. All right, let's move forward. Verifying identities involving double angle formulas. Some identities include one or more double angle identities. We identify these new identities using techniques learned in section 5.2. For example 13, verify that 2x equals 2 cotangent of x over cosecant squared x. All right, so for this one, let's manipulate the right side expression only. Let's work with this one right here. All right, let's begin by splitting our two fractions. Okay, and whenever you're in a position where like, okay, what do I do next? Write it as sine and cosine. So cotangent can be cosine of x times sine of x, and cosecant squared can be sine squared over 1. All right, we see that one of our sines cancel, and we're left with cosine times 2, and that looks like our double angle formula for sine. So we have proved our answer. Let's skip in class example 14. Let's do in class example 15. So we want to verify that sine of 3x equals 3 sine of x minus 4 sine cubed of x. And we have a hint. Manipulate the left side using the sign of a sum, sine of 2x plus x. All right, so it wants us to manipulate using that hint. Let's start with that side. Okay, let's work this out. So I can think of sine as sine of 2x plus x. Let's look back at our formulas from 5.2. And I'll write above your formula for the sine sum formula is sine A times cosine B plus sine B cosine A. All right, so if this is A and this is B, I can expand it to be sine of 2x times cosine of x plus sine of B, which is x, times cosine of 2x. Does that help? I can't see how this would help. Maybe I can work with the right-hand side. Three sine of x minus 4 sine cubed of x. I can factor a sine. I don't see how that would help. 3 sine of x would give me 3 minus 4 sine squared of x. Oh, I think I get it. I think I see what's going on. I think what they want us to do is our double angle identities. So then I can make these, use those using our double angle identities, right? So sine of 2x, that would be 2 sine A, or 2 sine x times cosine x times cosine of x plus sine of x and cosine of 2x. Cosine of 2x, which one do we want to use? We have options. We want to have more signs because we want to assign cubed. So let's go ahead and maybe use cosine squared A times minus sine squared A. Cosine squared A minus sine squared A. Maybe 1 minus 2. I think I want to use the 1 minus 2. 1 minus 2 sine squared of A. All right, let's go ahead and multiply. So sine times 1, and I have 2 cosines, so that's 2 sine cosine squared x plus, here I have to distribute. I'm left with sine x minus 2 sine cubed. We have x's, right? X. All right. Above, we only want sines, so we don't want this cosine squared. Luckily, we can use our Pythagorean identity. This is really hard. So cosine squared is the same thing as one minus sine squared. One minus sine squared. So we're left with 2 sine of x times 1 minus sine squared of x plus sine of x minus 2 sine cubed of x. We have to distribute in the sign. We have 2 sine of x minus 2 sine cubed of x plus sine of x minus 2 sine cubed of x. Let's combine like terms. I have a cubic and a cubic. So we have negative 4 sine cubed of x. You have a sine of x and a sine of x. 2 plus 1, 3 sine of x. That's what we have above. Yep. 3 sine of x minus 4 sine cubed of x. Whoa. My brain is fried. All right, so let's go over this one again. It was a proving problem, and it gave you a hint. It said treat that sine cube, sine 3 of x, using your new sum formulas. Okay, so you take the time to rewrite it. Okay, at this moment I was stumped. I kind of didn't notice, hey, I can use my double angle formulas that we learned. I have a 2x and a 2x. We have formulas that let us work through those, okay? And I did those in red below. All right, sine of 2x the same as 2 sine of x times cosine of x. And I write times cosine plus sine of x, and cosine of 2x the same as 1 minus 2 sine squared of x. You have options for cosine of 2x. You can pick whichever one you want. You can, in between, you would just use Pythagorean theorem to work through the one that wasn't the best choice. Okay, so as you're looking into our goal, always keep your eye on what you want. We want 3 sine of x minus 4 cubed of x. So I only want sines. I need to get rid of my cosine. Well, I can change my cosine squared of x that I got from multiplying cosine of x times cosine of x. I can use my Pythagorean identity. So I'm left with 1 minus sine squared of x. All right, now I need to distribute into our parentheses at 2 sine of x. And we're left with 2 sine of x times 1 is 2 sine of x. 2 sine of x times sine squared of x, I have now cubic. 2 sine cubic of x. And then we combine like terms from there to get our final answer.
How does 2 sine x minus 2 sine cubed come to negative
Oh,
4
okay.
sine cubed?
Oh, I'm combining like terms. So from there, you want to group your cubics. So I have cubic right here and right here. So negative 2 minus 2, we get that negative 4. 4 sine cube of x. So it would be the same thing as saying maybe like negative 2x cubed minus minus 2x cubed. Wouldn't that give us negative 4x cubed? But now we have a sign. And same thing with the signs. 2 sine x plus sine x. That would be the same thing as, you want to think of it as 2x plus x. That gives us 3x. And that's where we get this 3 sine x.
Okay, got it. Thank you.
Yeah. And then you want a certain order according to what we want. So we can just flip the order. All right, so let's do some examples from your homework. So for your homework, I want you to do did I skip something? We don't have anything for tangent that I remember talking about. Did he ever give us a tangent formula? Oh, we mentioned it, but never did an example. Okay, so let's do an example before we take off. But let me tell you your homework. Your homework will be all odds.
You said all odds?
All odds.
Alrighty.
Yeah. So let's do some before we end this section. All right, so let's do let's do 3 before we leave. I want to do more. I don't just want to do 3. I also want to do 9. 19 and 29. All right, so I'll give you 10 minutes to try those problems. So the numbers I said we were going to do together before we finish this section are 3, 9, 19, and 29. All right, so give those a try. I'll come back in 10 minutes so we can do them together, but take 10 minutes to do numbers 3, 9, 19, and 29. Just so we get some practice. Think maybe we can go over them together. So I'll have the Zoom on as we're working with these in case you have a question, you can ask it, but I'm going to mute myself so I can go grab a snack. All right, let's go ahead and continue. Let's work through these problems together that I asked you to try. All right, so number 3. We have some instructions, and our instructions say find both 2 sine of A and cosine 2A. And we have an outline to follow. Okay, so we're told that we're in quadrant 3. Always draw your quadrant, your triangle, because it's going to help you figure out your x and your y's. Because your x is on the left side, it should be a minus. Your y would be a minus, and your r is always positive. Okay, so we're given secant of A, and secant is the reciprocal of cosine. So cosine of theta is x over r. So therefore, secant of theta is r over x. Okay, so we're given r and x. X has a negative. And we would know that also from our picture above. So x is -3. R is radical 10. We have to find y. We don't know what that is. We go on to our second block, 2, to find y. We use our Pythagorean theorem, x squared plus y squared equals r squared. X is -3, so -3 squared plus y squared is equal to r squared, square root of 10 squared. So we have 9 plus y squared is equal to 10. We subtract 9 on both sides. Y squared is equal to 1. So y is equal to plus or minus the square root of 1. We know that y needs to be negative. So we choose -1. Y is equal to -1. Okay, so cosine, which is x over r, and sine, which is y over r, we now have the pieces to find that value. So cosine is x, -3 over r, which is radical 10. And sine is y over r. Y is -1, and r is square root of 10. Let's not rationalize it just yet because we don't know how it's going to affect our answer. This is just our work. Okay, so sine of 2a. Sine of 2a is 2 sine of a times cosine of a. This is the formula that we developed for this section. Okay, let's fill in these pieces. 2 times sine of a. Sine is -1 square root of 10 times cosine of a, and cosine is -3 over square root of 10. All right, negative times a negative is positive. So we're left with 2 times 1 times 3 over square root of 10 times square root of 10 is 10. So we have 6 over 10, which is 3 over 5, once we simplify. Okay, cosine of 2a, you can pick any of the ones you have. You have 3. I'll use 1 minus 2 sine squared of a. So I have 1 minus 2 sine squared of a. You could use a different one. Your answer will still be the same. So I have 1 minus 2. And sine is -1. Ooh. -1 over square root of 10 squared. All right, so we have 1 minus 2. And we have 1 over 10. Now that it's been squared. So we have 1 minus 2 over 10. 1 can be 10 over 10. Minus 2 over 10. We're left with 8 over 10. Simplify, you get 4 over 5. All right, so that's 3. I also asked you to work on 9. Before I move to 9, are there any questions on 3?
No, ma'am.
I do. I
Cool
have a
beans.
question.
Yeah.
If you rationalize cosine and sine, does that change the answer that you get?
No, because if you rationalize, it's still the same number. It's just you would have a bigger number to simplify at the end. So you should still get the same thing even if you rationalized.
I rationalized. I came up with something entirely different. Oh yeah, whatever. Let's just move on, I guess.
All right, so double check your work. Remember when you rationalize. So if you chose to rationalize, then it would have been -3 times 10 over square root of 10 over 10. And this should have been negative square root of 10 over 10. So when you plug it in, you'll still have to multiply it by another radical. It's just at the end, before you get to the very last step, you should have a bigger fraction to simplify. That's the only thing that should be different.
I ended up with these, with the cosine and sine being correct, but for some reason my final answers were not correct.
Try them one more time. Maybe it was a silly calculation error. All right, let's go on ahead with 9. Find tangent of 2a when tangent of a is 1/2. All right, so tangent of 2a, we have that formula, and our formula is, we have tangent of 2a is equal to 2 times tangent of a over 1 minus tangent squared of a. And we're told that tangent a is 1/2. Maybe he should have made that a capital A. So we're just replacing our tangents with a negative 1/2. So that we have 2 times negative 1/2 over 1 minus negative 1/2 squared. So in our numerator, we're left with -1 over 1 minus 1 over 4. We can write that as 4 over 4, so we get 3 over 4, -1 over 3 over 4. So that's -1 divided by 3 over 4, which is -1 times 4 over 3. So our answer is -4 over 3. That's A. Let's go ahead and look at 19. Multiply and divide to create a double angle identity. Okay, so for 19, as we're looking at my double angle identities, which one has sine and cosine? Well, my sine 2a, right? We have that sine 2a is equal to 2 times sine of a times cosine. All right, well, I'm missing that 2. So what can I do? I want 2 sine of 165 times cosine of 165. I got that 2. Now I must also multiply it by 1/2. So I added that 1/2 and that 1/2 times 2. Okay, let's focus only on the part we want to work with. So let's put brackets on it. Okay, now I have my double angle identity. So I can think of this as sine of 2 times 165. So that is sine of 165 times 2. You get 330. And sine at 330 we get -1/2. Now we have to multiply that 1/2 that we had in the front. So our final answer is -1/4. Any questions on 19?
I have a question.
Uh-huh.
Why I still don't understand why we're multiplying it by half if the 2 is already part of the formula.
Right.
Like, yeah.
So the 2 is part of my formula. Do you have a 2 in your problem?
No.
No, right? So we're missing that 2. So what can I do to make that 2 appear? That's kind of what we're saying.
Oh,
What
okay.
can we do to make that 2 appear? Well, to make it happen, I don't want to change the value of it, because if I have $4 and I multiply it by 2, I have $8. So $4 and $8 aren't the same. What can I do so that I don't change the value, but I still have that 2? So we multiply it by a 1/2 and a 2.
Okay. Got it.
I
So
know
is
it's
there
weird.
are there problems where it's gonna come with the 2 in the problem, or that never
In your
happens?
homework, yeah, you'll have that in your homework. Sometimes you won't always be a 2. Sometimes you're missing a -1. So you have to add and subtract a 1.
Okay.
And you'll do this like a lot in your second calculus course when you're working with weird integrals.
Mm,
Professor, really quick before you move on, can you just go back to number 9 for a second? I was just looking over it. I have one last thing to write down. Sorry.
Oh, yeah. You can
All right.
screenshot it from
Yeah,
your desktop.
Okay. I got it. Thank you.
Yep.
And I actually needed some help again on number 19. Where, as far as the distribution goes, like what happened to the cosine of 165?
Okay. The whole purpose of this, do you see on top how we have 2 sine of A, cosine of A?
Yes.
So 165 is not a number in your unit circle. We go from 150 to 180. So it's not a number I can work with. But you can use your sine of 2A, and they're equal, right? So this is saying that if A is 165, I can multiply it by 2. So that's why we do this part right here when we multiply it by 2. If I multiply it by 2, 2 times 165, we get 330. And that's a number I can work with because that's a value in a unit circle. So far, at this moment, it's like we only have a unit circle. There's no such thing as a calculator. So how can we work through these problems?
So are we
Okay.
pretty much ignoring the cosine of 165?
Well, what is cosine of 165?
It's not on the unit circle.
Right, it's on the unit circle. So what can we do? Well, I have this, right?
Mhm.
I can go ahead and multiply my A times 2. And that's what we're doing here. So I multiply 2 times A and we get 330. Now I can work with sine of 330. So we're not using them separately. Sometimes we have to make it look like that so I can use my other side of my equality.
I'm still not 100% sure what we're doing here.
Okay, so the whole purpose of this is we created these formulas, or we proved these formulas. And the idea is, how can I rewrite something so that A, I can evaluate for it, or B, create a shortcut. So we're not really using the shortcut portion of this just yet. You use that more in your calculus class when you have something you want to work with, but it doesn't look right. So how can I change things? That's when these trig functions come back to haunt you. For now, we're just using them as, hey, these two things are equal. Well, if I know they're equal, I can use them interchangeably. So because I have 2 sine of 165 times cosine of 165, that's this part right here. Now I can't solve for that. I can't solve for that because I don't have 165 in my unit circle. However, we're saying it's equal. That equality is very powerful. So I can use the other side of it. It's the same thing as 2 times A. So I'm going to multiply 165 times 2, and I only use a sign. So sine of 2 times A is 165. Now I can work with sine of 330. Can we work with that? Yeah, well, that is a value in my unit circle, so I can work with that.
So why do we even bother writing the cosine of 165?
Because that's your problem, that's given. Right? Your problem is cosine of 165 times sine of 165, and we want to evaluate. Well, I don't know
But
what
if we can't use the cosine of 165, why are we bringing it with us further down the problem, I guess?
Oh, okay. We're bringing it down with us because it's part of your formula. It's attached together. You can't break it up. Your formula is 2 sine of A times cosine of A. That's the right side of your formula. You can't just drop the cosine because you don't want it. You need to have it because with that together, I can say that that is equal to sine of 2A. And by having 2A, I can double it. And now it's a value in my unit circle. And that's the whole point.
But we don't do any distribution to it of any kind?
No. Distribution happens when I have A times B plus C. We have to be adding two numbers, and then we can distribute the outside.
Right. But we're not working at all in this problem with the cosine of 165. There's nothing going on with it. It's just sort of there.
Power formula, maybe that's a better way to say it.
So our actual work is being done on what then? It's just being done on the 165?
Yeah, on doubling the 165.
Okay. So we can just ignore the sine and cosine, and it's just, we're essentially just doubling 165.
Yeah.
Okay.
All right. Yes. Uh-huh.
I think my problem was the way you trying to figure out how you got from 2 sine 165 and cosine 165 to sine and then 2 times 165. That was my problem.
Okay. Well, we're treating your 165 as your A, right?
Mm-hmm.
So in our formula, this is our formula. I have cosine, sine of A times cosine of A, but I'm missing that 2. Right? So I multiply by a 2. But if I multiply by just a 2, just for kicks, it changes your whole problem. But I can multiply by 1 without changing the value of it. So to compensate, you multiply it by 1/2. Because 1/2 times 2 is 1. And 1 times anything is itself. So we're not changing the value of it. The whole purpose of this was so that we can have 2 sine of 165 cosine of 165.
Oh, okay.
That's the whole purpose, because then I have my formula. I have 2 sine of A, which is 165, cosine of 165. All right, now that I have my formula, I can use the equality. I can use this side. I can rewrite it to be sine of 2 times 165. My A is 165. The reason for this is because 2 times 165 is 330. Now I can use my unit circle. So sine at 330 gives me 1/2. We have that here. And now I can bring down that 1/2 I've been ignoring the whole time and multiply it to my answer.
Oh, okay, I get it now.
Cool, I'm glad you got it.
Thank you.
I know these are really tricky. I remember just being like, what are you compensating?
Yeah.
I was thinking like a little man driving a really big truck, which is really sexist and inappropriate, but that's always what I think about. Like compensating. I don't know. That's inappropriate. Okay. Yeah.
Are you still gonna upload these to YouTube?
Yeah, they've been uploaded onto YouTube. Everything's on YouTube.
All right, cool. Thanks.
It'll be up in like an hour.
All right, cool. Thank you.
By the way.
All right. And I say an hour because it takes like a half hour for me to get to Zoom, and it takes almost like 40 minutes to upload onto YouTube. It takes a long time. All right, 29. 29, what does your instructions say? Verify each identity. Manipulate only one side. All right, these are my favorite because they make my brain hurt. They make you work. They make you think. All right, so 1 minus cosine of 2x over sine of 2x is equal to tangent. So you always want to work with the side that looks like work can be done, so your more complex side. And we see that the left-hand side, there's work to be done, right? Okay, so let's go ahead and recall our identities. So I have 2 I can use I have 3 for cosine and 1 for sine. Doesn't matter which one you pick, because if it's not what you want, you can use Pythagorean identities to move back and forth. So we have that cosine of 2a is the same thing as cosine squared minus sine squared. And sine 2a is equal to 2 sine a times cosine of a. And we're going to replace these with these right here, right? So instead of 2x, I'm going to write cosine squared x times sine squared x. I forgot the name, but we're going to be using x. All right, so let's make that replacement. So I have 1 minus, and I have cosine squared of x minus sine squared of x divided by sine 2x will give us 2 sine of x cosine of x. All right, I want to get tangent from this. And I have a 1 that I don't need to work with. So maybe I can use my Pythagorean identities, right? So I know tangent. I'm just going to keep this in mind. I'm going to write it. I know tangent is sine over cosine because we have all these sines and cosines. So I want to keep my sine on top. So maybe I should change this to one of our Pythagorean identities. And cosine squared is the same as cosine squared theta is 1 minus sine squared theta. So let's replace that. So that I have 1 minus, I now have 1 minus sine squared theta, or x, and I still have that minus sine squared x, all over 2 sine x cosine x. Okay, cool. Well, 1 minus 1 is 0. So let's rewrite our problem. We're left so far with negative sine squared x minus sine squared x is equal or over 2 sine x cosine x. Well, I can combine like terms in the beginning, right? And just to help you out, negative 2x squared minus 2x squared gives you negative 4x squared, right? Negative 4x squared. So treat x like your sign. So our numerator, we now have negative 2. Negative 2 sine squared x. My denominator, I have 2 sine x, cosine x. All right, well, my 2's can divide out. And my signs divide, so I have my sign gone. That's now assigned to the first power. And so far, I have negative sine of x over cosine of x. And how to get rid of that negative? Oh, I see what happened. I have a slight sign error. So we're replacing cosine with that in yellow. We should put brackets. So I can distribute my sign. So we have to erase our work. So we now have 1. Well, I guess we don't have to subtract over on the side. So we have 1 minus 1 minus 1 plus sine squared of x minus sine squared of x. So those are gone. Now we're left with 0 in the numerator.
So you distributed the 1?
The negative,
Oh, just the negative? Okay.
just a negative. Let's start over. Let's start over. That's okay to do in your math problem. It's okay to start over. Okay, everything else we need. So at least we have a right train of thought. So I have 1 minus, that's another one we have to do. Cosine squared a or x minus sine squared x all over sine 2x is 2 sine of x cosine of x. Now I see that big mistake. We were supposed to distribute into our first cosine, that negative. So that we have 1 minus cosine squared of x plus sine squared of x. There we go. And you can proceed the same way like we did. Okay, I want to get rid of my cosine, so let's replace that cosine with the Pythagorean identity. Cosine squared theta is the same thing as 1 minus sine squared theta. So we have 1 minus, we're going to use a bracket to replace it. 1 minus sine squared x plus sine squared x all over 2 sine x times cosine x. Again, we have to distribute our negative, just our negative value, and we're left with 1 plus or minus 1 plus sine squared x plus sine squared x all over 2 sine x times cosine x. 1 minus 1, that's 0. So we're left with sine squared x plus sine squared x. We get 2 sine squared x all over 2 sine of x times cosine of x. All right, 2 divided by 2 is 1. Sine squared divided by sine x. Simplify so that we're left with sine of x over cosine of x. And that gives us tangent of x. So we had now proven that tangent of x is equal to tangent of x. We were on the right track. There was one small sign error in the beginning, and that threw us off so that we had an extra negative. Alrighty. So there's some I wanted you to try before we left. Now we've been together for 2 hours. I think that's more time than I ever want to spend on a Zoom meeting. So I'll leave.
Sorry.
So I'll leave the 136 correct problems for you to try. So you're gonna email with some problems to try. They're factoring problems. Factoring will be heavily used in section 6, so chapter 6. So make sure you take a chance to look over those worksheets. Maybe I'll go over them in the beginning of our next class, but make sure you make it a point to at least look at them. They're on factoring.
Are there assignments for the correct class that we are supposed to have been working on?
Yes and no. So I passed them out. I passed them out in the beginning, and I meant to collect them or give you credit for them, and I never made a point to. So maybe I'll make you upload those files, or I don't know. I kind of fell off of working on the correct stuff once we transitioned to online, mainly because I don't know. I wasn't prepared to go online like everyone, right? It wasn't something I first saw happening. So maybe I'll find videos that match up those worksheets, and I'll start making you turn them in maybe like 2 a week, so I can start developing a grade for your 136 course, because I still need to give you a grade for that one separately from your trig course.
Professor, was that a grade itself, or was it a pass-fail class?
Pass, no pass.
Okay.
I need to develop to give you a pass or a no pass. There's a final. I can just make it based on the final if you don't want to worry about turning in stuff.
As long as there's review material, I'm fine with that.
Yeah. Okay, we can do that then. Yeah, there is a review. I'll give you a review once you get closer to your 136 final, which is in week 15, and we're in week 11, I believe. So you have a month till your correct final. Your 136 final is scheduled for May 28th. So exactly a month from today. So maybe like around week 13, I'll start going over review material, but I'll start posting videos that will help you for, at least for now, for factoring, which is what you need for chapter 6. All right, I'll go ahead and do that then. All right, so that's it for today. I'm sorry we went for so long. I know it must be so tiring to be in front of your screen, just trying to see my writing and match up to what I'm saying for 2 hours straight. I'm so sorry.
Thank you, Professor. See you next on Thursday.
Thank you for being here with me. Have a nice day, all of you.
Take care.
too.
Also, I responded to Andrea on her homework. Thank you. She asked me, and I did. I knew most of them are odds, but I wasn't keeping track. So I'll copy those down for myself. All right, so that's it for today. I'm going to go ahead and log off. You can go ahead and log off as well, unless you have some questions. All right, have a nice day. I'll see you on Thursday.